Every single day, trains across the world rely on more than 1.6 million kilometers of railway track. Enough to circle the Earth 40 times. And each mile of that track requires massive steel rails, each weighing over 60 kilograms per meter. That means a single mile of railway line uses nearly 100 tons of solid steel rails. Global demand for rails exceeds 20 million tons every year. And every single rail must be manufactured with extreme precision, able to last decades under the crushing weight of trains that can weigh over 20,000 tons. So how are these supergiant steel rails made? Today, we're uncovering the mind-blowing process of making train rails, the very backbone of modern transportation. The story begins deep underground. The steel for train rails starts as raw materials: iron ore, coal, and limestone. Iron ore is mined from huge open-pit mines in countries like Australia, Brazil, India, and the United States. Coal is baked into coke, a purified form of carbon used to fuel blast furnaces. Limestone is mined to act as a flux, helping remove impurities. Massive haul trucks, some carrying 400 tons in a single load, transport the ore to crushing plants. Conveyor belts move the material for kilometers before it's shipped by train or cargo ship to steel plants. Just think, the largest iron ore mine in Brazil produces over 100 million tons every year, enough to build rails that could wrap around the globe multiple times. At the steel plant, the raw materials face their fiery transformation. The blast furnace, towering over 100 feet tall, is charged with layers of coke, iron ore, and limestone. From the bottom, superheated air at 1,600 degrees Celsius, 2,900 fever, is blasted in at high pressure. Inside, the coke burns, releasing carbon monoxide that strips oxygen from the iron ore, leaving behind molten iron. Impurities float to the top as molten slag, while rivers of glowing liquid iron sink to the bottom. Every few hours, workers tap the furnace, releasing streams of orange-hot iron into giant ladles. Each tap produces 300 tons of molten iron, enough for nearly 3 kilometers of railway track. It's a breathtaking sight. Steelworkers guiding rivers of liquid fire that will one day carry the weight of trains across continents. Molten iron on its own is too brittle. To make train rails, it needs to be converted into special rail-grade steel. Each batch is carefully monitored with sensors and chemical analysis. A rail steel must be strong enough to endure 1.5 billion gross tons of traffic over its lifetime, but flexible enough not to crack under sudden impact. Think about it. Every time a train wheel slams onto a rail joint at 200 kilometers per hour, the steel absorbs forces equivalent to several tons concentrated in a tiny spot. Only perfectly engineered steel can survive this punishment for decades. The purified steel is poured into a continuous casting machine, one of the most mind-blowing technologies in steelmaking. The molten steel enters copper molds cooled by water, solidifying into long rectangular shapes called blooms. These blooms, glowing cherry red, can weigh 10 tons each and stretch 40 feet long. Every bloom is marked with an ID code, linking it back to the batch of steel it came from. That way, if a problem ever appears in a rail years later, engineers can trace it all the way back to the day it was cast. Some modern plants can produce rails up to 120 meters, 394 feet in a single piece, the length of a football field. These ultra-long rails reduce the number of joints in the track, making trains run smoother and faster. Rails endure some of the harshest conditions in engineering: freezing winters, scorching summers, and the constant pounding of heavy trains. To survive, they undergo heat treatment. The rails are reheated, then rapidly cooled in a controlled process known as quenching. This hardens the surface to resist wear while keeping the inner core tough and flexible. A treated rail can last 30 years or more on busy lines. On high-speed railways, rails are replaced after 1.5 billion gross tons of traffic. That's like carrying the weight of 10 million elephants before showing signs of fatigue. Safety is everything in railways. If a rail fails, it's melted down and recycled. Only flawless rails are shipped out. Imagine moving a 120-meter steel rail. Special railway wagons, sometimes stretching half a kilometer long, are designed just to carry them. In some cases, rails are welded together at the factory into even longer sections, creating continuous welded rail. These rails reduce the familiar clickety-clack sound of trains and allow smoother rides at higher speeds. At construction sites, massive machines called rail layers lift the giant rails and place them onto sleepers, railroad ties. Crews bolt and fasten the rails with clips and plates, ensuring perfect alignment. For high-speed trains, alignment is so precise that even a 1 millimeter error over a kilometer of track can cause vibrations at 300 kilometers per hour. That's why lasers and GPS-guided machines are used to ensure perfection. Steel is one of the most recyclable materials in the world. Old rails, after decades of service, are collected, melted, and reborn as new rails. This saves enormous amounts of energy. Recycling steel uses 75% less energy than making new steel from raw ore. It also reduces emissions, making railways one of the most sustainable forms of transport. Picture this: a rail forged in a steel plant in Pennsylvania in 1990. For decades, it carried coal trains across the Appalachian Mountains, each train weighing 15,000 tons. Snowstorms, summer heat, countless wheels grinding its surface. After 30 years, engineers replace it. But instead of being thrown away, it's shipped back, melted down, and cast into a new rail. Today, that very same steel might be part of a high-speed line in California, carrying passengers at 200 miles per hour. The life of a rail is never over. It simply transforms. If you enjoyed this deep dive into the mind-blowing world of rail steelmaking, don't forget to hit like, subscribe, and turn on the bell. We've got more epic journeys into the world's biggest industries coming soon. And trust me, you don't want to miss them. Every day, millions of machines quietly keep the world running. Electric cars, elevators, washing machines, industrial robots. At the core of nearly all of them lies a single essential component: the electric motor. But what powers the motor itself? How is it made, and where do the raw materials come from? In this documentary, we step inside a state-of-the-art facility to uncover the full journey, from recycled metal scraps to precision-engineered electric motors. It's a story of molten metal, spinning copper coils, cutting-edge robotics, and sustainable innovation. You'll witness how scrap metal is recovered, melted down, and reshaped, and how advanced manufacturing techniques transform these raw elements into the motors that drive modern life. This isn't just about engineering, it's about the future of power, production, and the circular economy. This is the incredible manufacturing process of electric motors and the metal recycling revolution behind it. Every electric motor begins its life not on an assembly line, but in the scrapyard. Tons of discarded metal, from old appliances, demolished vehicles, and industrial waste, arrive at recycling centers every day. What once was broken and forgotten is now seen as raw material for the next generation of machines. The first step is sorting. Using powerful magnets, conveyor systems, and infrared scanners, metal is separated by type: ferrous from non-ferrous, steel from aluminum, and copper from brass. Precision is critical. Even a small impurity can affect performance in later stages. Once sorted, the metals are cleaned of dirt, oil, and coatings. Then they're shredded into smaller fragments and sent to furnaces where they're melted down. Aluminum melts at around 660 degrees Celsius, copper at over 1000 degrees, and steel at an even higher temperature. Inside the massive induction furnaces, the scrap metal becomes molten, glowing with intense orange heat. Impurities rise to the surface and are skimmed off as slag, leaving behind purified metal, ready to be reborn. The molten metal is cast into standardized forms, rods, sheets, or billets, depending on the motor component it's destined to become. Aluminum may be rolled into housings, copper into winding wire, and steel into rotor shafts. Before these materials even reach the motor assembly line, they've already been through fire, force, and filtration. It's a transformation few see, but one that underpins every step of modern manufacturing. The journey from junkyard to high-performance component has only just begun. At the center of every electric motor are two vital components, the stator and the rotor. Together, they form the beating heart of the machine, converting electrical energy into mechanical motion with remarkable efficiency. Once the raw materials have been purified and shaped, they move into the precision engineering phase, where each part is carefully manufactured to tight tolerances. Let's begin with the stator, the stationary part of the motor. It typically consists of laminated steel sheets stacked together to form a hollow cylinder. These sheets are stamped with slots that will later house copper windings. Lamination is crucial. By stacking thin layers instead of using a single block of metal, the motor reduces energy loss caused by eddy currents, improving overall efficiency. The stator core is placed in an automated winding machine. Here, insulated copper wire, usually made from 99.99% pure recycled copper, is wound into tight, uniform coils that fit into the slots. These coils are not randomly wound, they follow a precise configuration based on the motor's design. Whether it's a three-phase industrial motor or a small DC motor for a household appliance, the winding pattern defines how the magnetic field will be generated. After winding, the coils are dipped or sprayed with varnish, then baked in industrial ovens. This insulation process ensures that the wires remain fixed and protected from moisture, vibration, and heat during operation. Next comes the rotor, the rotating part of the motor. Depending on the type of motor, it may consist of solid steel shafts, laminated cores, or even cast aluminum squirrel cage designs. In induction motors, for example, molten aluminum is injected into molds around a rotor core, forming conductive bars that interact with the magnetic field from the stator. Balancing is critical at this stage. The rotor must spin at thousands of revolutions per minute without wobbling. High-precision machines check for even the smallest imbalance. If necessary, micro-adjustments are made by shaving material or adding weights to achieve perfect symmetry. Bearings are then installed on each end of the rotor shaft. These reduce friction and allow smooth rotation while also handling the mechanical loads during operation. Depending on the application, the bearings might be sealed, ceramic, or even magnetic for ultra-low resistance performance. Once the stator and rotor are completed, they undergo separate quality control inspections. Electrical tests check for coil resistance, insulation integrity, and potential short circuits. Mechanical tests verify alignment, dimensional accuracy, and overall structural soundness. It's only when both components pass all tests that they move to the assembly phase, where the motor will finally take shape. Building stators and rotors is not just about metal and wire. It's about precision, durability, and an invisible choreography of electromagnetic forces. Because inside every electric motor lies a symphony of motion, and it all starts with these two elements, engineered to perfection. With the stator and rotor meticulously prepared, it's time to bring the electric motor to life. The assembly process begins in a clean, organized line where each component is carefully fitted together. The stator is mounted into the motor housing, a protective shell made of cast aluminum or steel, often die-cast from recycled metal. Next, the rotor is gently inserted into the center of the stator, ensuring a precise air gap between the two. This tiny space, measured in fractions of a millimeter, is critical for the motor's efficiency and torque output. Once aligned, end bells, bearing caps, and cooling fans are installed. In larger motors, sensors are embedded to monitor temperature, vibration, and performance in real time. Now comes the moment of truth: testing. Each assembled motor undergoes a series of rigorous quality control checks. First, it's powered on and run through various speed and load conditions. Engineers monitor electrical consumption, heat buildup, and vibration levels. Any irregularities, such as excess noise or current imbalance, trigger a full diagnostic. For motors used in sensitive environments like aerospace or medical devices, testing becomes even more intense. Motors may be subjected to simulated environments, high altitudes, extreme temperatures, or continuous 24-hour runs to validate durability. Only motors that meet or exceed performance standards move on to final packaging. Those that fail are flagged, disassembled, and either corrected or recycled. Every motor that leaves the line is tagged with a serial number and logged in a database for traceability. Whether it's destined for a factory floor, an electric scooter, or a wind turbine, one thing is clear: its journey from scrap to spinning power is nothing short of extraordinary. Every factory generates waste: offcuts of aluminum, worn-out copper wire, broken bearings, and defective components. But in modern manufacturing, waste is no longer the end of the line. It's the beginning of something new. Metal recycling is not a side process. It's a central pillar of sustainable industry. In the electric motor factory, a dedicated section is designed solely for collecting and processing metallic byproducts. The process begins with collection. Every scrap, from a trimmed copper wire to a rejected steel shaft, is sorted and deposited into labeled bins. Workers and machines collaborate to separate materials with precision. Copper, aluminum, and steel are never mixed. Even slight contamination can compromise the integrity of recycled alloys. To speed up sorting, advanced detection systems are used. Induction sensors, X-ray fluorescence, XRF scanners, and automated vision tools identify metals based on density, conductivity, and chemical composition. These high-tech systems reduce error and maximize recovery. Once sorted, the metals are prepared for shredding. Large industrial shredders chew through hardened parts and tangled wires with ease, breaking them down into uniform chunks. The goal isn't just reduction, it's surface area. The smaller the pieces, the easier it is to melt and purify them later. After shredding, magnetic separators remove any ferrous contaminants from non-magnetic metals. Then eddy current separators isolate aluminum, and density-based systems sift out copper. The result is a clean, sorted stream of valuable raw material, ready for resmelting. But recycling doesn't stop at sorting and melting. Inside the furnace, these metals undergo a second transformation. Recycled copper is refined to 99.99% purity, good enough for electrical-grade wire. Aluminum is cast into ingots or extruded into new housing components. Steel is alloyed and rolled back into rotor shafts and fasteners. The energy required to recycle metal is a fraction of what it takes to mine and process virgin ore. Recycling copper, for example, uses up to 85% less energy than mining. That translates into lower emissions, reduced environmental impact, and more sustainable production overall. What's more, metals can be recycled infinitely without losing their core properties. Unlike plastic or paper, which degrade over time, copper, steel, and aluminum retain their strength, conductivity, and resilience through countless cycles. This circular approach turns the factory into a closed-loop system. The waste of today becomes the resource of tomorrow. Scraps are reborn as stators, rotors, casings, and eventually, as fully functional motors powering the next generation of devices. Recycling also protects supply chains from raw material shortages. As global demand for electric motors grows, driven by electric vehicles, renewable energy, and automation, reliable access to copper and rare metals becomes crucial. Recycling helps bridge the gap. It's not just good economics, it's smart engineering, and a powerful way to align manufacturing with environmental responsibility. In the end, every spinning motor tells a deeper story, not only of precision mechanics, but of a cycle that keeps resources in motion, just like the rotor it powers. At the heart of metal recycling lies one of the oldest and most awe-inspiring processes in human industry: melting. In this chapter, we enter the fiery core of the factory, where scrap metal is reborn in furnaces hotter than volcanoes. Once sorted and shredded, metals are sent to their respective smelting stations. Each type of metal requires different treatment. Copper is melted in induction furnaces that reach over 1,100 degrees Celsius. Aluminum melts at around 660 degrees Celsius, while steel demands temperatures exceeding 1,500 degrees Celsius. These furnaces are no ordinary ovens. Using electromagnetic induction, massive coils generate high-frequency currents that heat the metal rapidly and evenly. Inside, the shredded pieces glow and liquefy, forming a swirling pool of molten metal.